Welcome friends. In the previous lectures we have discussed radiative heat transfer between flat surfaces. We discussed black surfaces, we discussed grey surfaces. We also solved a number of numerical problems for which analytical solution was easy to calculate. We also introduced the method of electric networks to find a solution for the grey surfaces, but these methods, the electric network method and the analytical method, may not be applied when we are dealing with a large problem. A large problem with large number of enclosure surfaces makes it difficult to solve these problems by hand. So, we have to either employ a computer, we have to go for some kind of numerical technique to solve these problems. So, in this lecture we will study a few of these techniques to solve problems where we have the size of the problem is large or where we cannot approximate the enclosure with flat surfaces. So, just a quick recap to what we have done. In an enclosure, the radiative heat flux Q at any location r. So, this is the vector of the location r. If we take it with respect to some kind of origin, the heat flux at this location is made up of two components. One is the emitted energy and one is the absorbed energy. So, this is the energy balance for a small element or at any location given by the vector r. In the bracket, in the second term, we have what we call irradiation. So, this is irradiation. Okay. So, for a grey surface we define radiosity J. So, irradiation can be written in terms of radiosity, that is the total energy leaving at any location is called radiosity. It has two components, the emission from the surface and reflection of any radiation coming onto that element. So, radiosity has two components, emitted component and reflected component, and we have to integrate over the entire enclosure with proper view factor. So, with proper view factor we have to integrate over the enclosure, and this will give you the total irradiation, total incoming radiation at surface dA from all the enclosure, and we may have also an external component of irradiation coming from outside the enclosure. So, this relation we have already discussed, and this relation reduces to EBR minus the second term, which is very similar to the previous term. The only thing is the epsilon and alpha for the black surface have value equal to 1, and the radiosity J will simply reduces to emissive power. Okay. So, these relations we have already developed. Now, we will see how we can basically use this method to solve for a large enclosure. Okay. So, in the previous lectures on grey and black surfaces, we have derived algebraic equations. We assumed that the enclosure, any enclosure can be divided into finite number of surfaces. Okay. So, this is approximation which sometimes is good, but sometimes it may give you wrong results. We will see when we cannot and we should not approximate the enclosure with flat surfaces, but for the time being we assume that the enclosure is approximated with flat surfaces. So, if there are n flat surfaces which we have divided the enclosure into, some of these surfaces have known heat flux value. So, some of the surfaces the Q is known, while on some other surfaces the temperature may be known, okay, and the heat flux may be unknown. So, let us say from I is equal to 1 to small n we know Q values, and for I is equal to n plus 1 to capital N, the temperature is known, that is emissive power is known, but the flux is not known. So, total number of unknowns will be capital N, and some of these unknowns may be heat flux and some of these unknowns may be temperature. So, we write our energy balance equation that we have derived earlier, we introduce a variable called Kronecker delta. So, delta I j is simply equal to 1 for I is equal to j and is equal to 0 for I not equal to j. So, this is just for computer notation, we have introduced this parameter. So, on the left hand side we have unknown fluxes for the unknown MSC power or the unknown temperature for the first n surfaces. On the right hand side we have known fluxes Q I, external irradiation and irradiation from the surfaces n plus 1 to capital N, for which the temperature is known. Okay. So, we can write down the energy balance equation in this form. Now, one thing to note here is there are total n variables here, small n variables here. So, first we are trying to solve for the temperature here, and once we know the temperature or the MSC power, we can calculate the heat flux for surfaces n plus 1 to capital N. Okay. Now, this equation can be written in matrix form A times E b is equal to small b, where the matrix A contains the coefficients on the left hand side. So, the diagonal coefficients we have I is equal to j. So, we have 1 minus f I j from the first term. Off diagonal elements will have I not equal to j. So, delta I j will be equal to 0. So, we have minus f I j terms in the off diagonal, and the E b vector contains the MSC power, the unknown MSC power for the first n surfaces. So, this will have dimension of n cross 1, this will have dimension n cross n, and the right hand side the vector B contains the known fluxes for the first n surfaces, external irradiation on the surfaces and irradiation from all other surfaces for which the temperature is known. Okay. This also has dimension n cross 1. Now, this is a system of linear equation which is very easy to solve. We can program this equation and we can apply any linear solver like Gauss-Seidel to solve for the unknown temperature or MSC power E b. Once the MSC power is known, we can find out the unknown heat fluxes by just substituting these values in the original equation. Okay. So, this was for the black surfaces. Okay. For the grey surfaces, similarly we can write down the energy balance equation. The only difference between black surfaces and grey surfaces is that the unknowns contain the heat fluxes. For some surfaces unknown may be heat fluxes, for other surfaces the radiosity may be unknown. Okay. So, the radiosity contains both reflection and the emission. Okay. So, we have to solve for the entire n surfaces simultaneously. We have to solve for this simultaneously for the entire n surfaces. So, as before we write the equation for the unknowns, the first n unknowns contain the unknown MSC power, the second term on the left hand side contains n unknowns. So, we have these n unknowns here in terms of the MSC power, okay, and the next n plus 1 to n unknowns contain the unknown heat flux as the variable. So, the total size of the matrix that we will form in this case for the grey surfaces will be capital N. Okay. So, we have to solve simultaneously for the unknown fluxes and the MSC power. Okay. So, right hand side contains the known terms. So, we can know the heat flux for the first n surfaces. So, the first term on the right hand side is known, external irradiation is known, and the last term on the right hand side is the MSC power, because the temperature for surfaces n plus 1 to n is known. So, this term is also known. So, again we write this as a system of linear equation Ax is equal to b, but this has a little expanded matrix. The matrix looks like this. So, this part of the matrix, this part of the matrix contains the view factors that relates to the MSC power. The first n terms contains MSC power as the unknowns, and the rest n plus 1 to n contains heat flux as unknown. Okay. So, similarly, the matrix structure is like this. The left corner, top corner contains elements which directly relates to the MSE power, as in the previous example of black surfaces. We have diagonal terms 1 minus Fii and off diagonal terms as Fij, while this part of the matrix, the right hand side of the matrix contains terms which relates to the heat flux. Okay. So, it has the emittance and reflectance appearing in the terms because it relates to the heat flux. Just looking at the equation, it will be clear that reflectance appears in the heat flux term and it does not appear in the MSE power term. So, this is the structure of the matrix. The right hand side again contains the known fluxes for the first n surfaces, external irradiation and known MSE power from surfaces n plus 1 to n, and we can apply the same or similar method for the system of linear equation to solve this type of problems. So, this is how we can basically write the energy balance equation for surfaces in an enclosure, which is an idealized case, and solve it on a computer. Okay. So, I again recap why we call it idealized enclosure, because we have divided the enclosure into number of finite surfaces, okay, which may not always be good in all type of problems. For example, if we have a surface, okay, and let us say we want to maintain or heat this surface uniformly over the entire area. We want, let us say, the temperature of this surface to be maintained at 1500 Kelvin, and we do not want that the temperature variation of this surface should not be greater than, let us say, 1 degree centigrade. So, that entire surface should be maintained at uniform temperature, and the surface is heated using some heater. Let us call this is heater plate, okay, and we want to heat this plate. So, this is plate to be heated and maintained at certain temperature uniformly. So, one thing that we should do is we cannot approximate the surface as single surface, because if we do it, then this will just give us an average heat flux or average temperature. But if we want to know the temperature variation along the plate, we have to take into account how the radiosity J varies along this surface. Okay. So, this J has to be calculated at each and every point, and we should not approximate this surface with finite width or finite dimension plates. Okay. So, we start with the same equation that we developed for the heat flux for a gray surface, the emitted part, the absorbed part, okay. And for black surface, this will be just equal to 1, and radiosity will be simply equal to MSE power. Now, if the MSE power is constant, if temperature is known, if temperature over all the surfaces is known, then the integral in this equation can be evaluated first, and then subsequently we can solve for the flux. So, please note, if the temperature at all the surfaces is known, we can solve for this integral before we solve for the flux. Okay. So, this integral part of the equation can be separated from the algebraic part, okay, and the equation becomes pretty simple. Okay. On the other hand, if we have heat flux as unknown, then definitely the problem is going to be complicated. So, if temperature is unknown, then we have basically a variable appearing in integral. So, we have a variable appearing in integral, and then it becomes an integral equation. It is not a algebraic equation anymore, it becomes an integral equation, and this fact is much more manifested in gray surfaces. So, for gray surfaces we write the same energy balance equation as we have done before, and we see that the unknown heat flux is appearing in the integral, unknown MSc power may also appear in the integral, although if temperature for some surfaces is known, then this integral can be evaluated very easily. So, the only unknown appearing in the integral will be then the heat flux. Okay. So, we have what we call integral equation in this cases when we are finding the heat flux by not dividing the enclosure into finite number of surfaces. The good advantage of dividing the enclosure into finite number of surfaces was to convert the integral equation into algebraic equation, but if we do not do that, we have to solve for the integral equation, and there are number of methods to solve this equation. This type of equation where we have a variable, let us say the unknown function phi, it can be radiosity, it can be heat flux appearing in the integral on the right hand side also. So, this equation, this type of equation is called integral equation, and this particular equation is called Fredholm integral equation of second kind. The k appearing in this equation is called the kernel function, the f is a known function, and phi r is the function that we want to evaluate. It could be radiosity, it could be heat flux. So, this Fredholm equation we need to solve if we want to find out the exact distribution of heat flux over the enclosure. So, there are number of methods, analytical methods are also possible and numerical methods are also possible, although the analytical methods are mathematically quite involved and time consuming. So, most of the time we prefer to solve these type of problems using numerical methods, and the numerical methods provide good accuracy also. So, in analytical methods we have what we call kernel approximation method, and in numerical methods there are many methods, but three most important methods used is successive approximation method, quadrature method, and variational methods or Galerkin method. Okay. These methods are basically used extensively to solve problems in gray enclosures. So, I will discuss the successive approximation method and quadrature method in this lecture. So, I just give you an outline of the kernel approximation method. The method when applied to real problems becomes, the mathematics becomes quite involved. So, I will not take an example of this method. The outline of this method is basically we approximate the kernel function, the k, using some kind of simple functions like exponential function or trigonometric function or hyperbolic functions. So, these type of functions are used, the series of this function is used to approximate the kernel function. Okay. And these functions are then substituted in the integral, and the integrals are then evaluated very easily by converting this by calculating the integral of these trigonometric or hyperbolic functions. The equation, the integral equation is converted into a differential equation which can be solved easily as compared to the integral equation. So, the method in itself is straightforward, but the solution of these integrals and the subsequent differential equation becomes quite involved. Okay. So, I will not take any example on this method. The next method is successive approximation method. In successive approximation method, this is a numerical method. What we do is we basically make a guess of this function, okay, and substitute this into the integral. Okay. So, for let us say we first guess that the distribution function for the heat flux or radiosity, the known function, is given by this function f. Okay. And we substitute this function into the integral and solve the integral either analytically or through numerical quadrature. So, we solve this in analytical or using numerical quadrature. Once the integral is solved, we get a new value of the function phi r. Okay. And then this value of phi r is again substituted into the integral, and the solution, a new solution is found. So, this is an iterative method. Okay. So, let me just again highlight. So, we have unknown function phi, which is basically given by K phi dr as is given here. We can just write down it as A. Okay. So, we first assume some value of, let us call phi I, and substitute it here and solve the right hand side. So, we get phi 2 as f plus k phi 1 dA. Now, this integral we can solve analytically or through numerical quadrature. Once this is solved, we get a new value of the function phi 2, and then we substitute it back. So, we get phi 3 is equal to f plus k phi 2 dA, and this keeps on keeps on doing this until we get a desired result. Okay. So, this method also is quite involved if we try to solve this an integral using analytical methods, but it can be an easy method if we use numerical quadrature to solve the integrals. We will do one example to demonstrate this method. In this case, we have two infinite parallel plates separated by a distance h. Both the plates are maintained at temperature T, and they are exposed to cold environment. That means, we are not including the effect of external irradiation. Both the plates are diffuse with emittance epsilon. So, we have to find out local radiative heat flux. So, we have to find out Q as a function of R on both the plates. Okay. So, this is the desired quantity that we are interested in. As is clear, we are not interested in average heat flux. Average heat flux we could have found by the methods we have already discussed. Okay. But we are interested in the actual value of flux as it varies over radius r. Okay. Although this problem we have taken is quite trivial due to the one dimensionality of the problem. It is an infinite plate. This dimension in the third direction is infinite. So, the result would be quite similar to the average values, but still as a purpose of demonstrating the method, this problem serves a good example. So, let us solve this problem. So, first of all, we write down the expression for radiosity. This is going to be gray diffuse surfaces. So, the problem involves gray diffuse surfaces. That means, the value of emittance is not equal to 1, and we have diffusely emitting and reflecting surfaces. Okay. So, we write down the radiosity surface 1 J1, which is going to be function of x. Okay. X is the coordinate along the direction of the plate, is equal to, and we can just emission and absorption. So, this is our radiosity. So, radiosity contains the emission term and reflection term. So, this is emission from the plate and this is the reflection from the plate. Okay. In this expression you might have noticed that we have only J2 appearing in this because there is not going to be irradiation from the same surface. So, we have F11 is equal to F22 is equal to 0. So, there is no self irradiation. So, the only unknown appearing in the integral is for the J2. Okay. Similarly, we will write this for surface 2 also. So, surface 2, the J2 value can be written as epsilon sigma T to the power 4. Both the plates are of the same temperature with same emittance 0 to W J1 dF dA2 to dA1. Okay. So, this is basically the relation. Now, we have to find out the view factors first. So, let us So, I will not do the view factor calculation, we have already done that, and this is a simple geometry. So, so view factor from lookup tables can be calculated. So, this value will be equal to dx1, we are trying to find out the small element view factor, dA1 to dA2 is equal to dx2 df dA2 to dA1. This is readily available from the lookup table, from the tables in the for the view factor, and this value is equal to h square dx1 dx2 h square plus x1 minus x2 square power 3 by 2. Okay. So, let me tell you what basically this represent. So, we have these two tables, we have a small element area at a distance of x1, the thickness of this is dx1, another area we have the distance from the left side is x2 and the area thickness is dx2. So, the view factor between these two surfaces is what we are basically talking in this case. Okay. So, now our radiosity relations are both very similar, the expression for J1 and expression for J2 are very similar. So, we are going to substitute for the view factors in this relation. So, for example, J1 x1, now we have introduced the specific x coordinate x1 for the plate 1 is equal to epsilon sigma t power 4 plus 1 minus epsilon 0 to w J2, let us call this x2, and df dA1 to dA2. Okay. So, df dA1 to dA2 will be equal to h square by 2 h square plus x1 minus x2 square power 3 by 2, and this will be dx2. Okay. So, as you see the integral is quite involved. Okay. So, we have to introduce some, so let us introduce non-dimensional parameters. Okay. So, we introduce non-dimensional parameters as w, capital W as w by h, and zeta as equal to x by h. Okay. So, these non-dimensional parameters we have introduced, and we have also introduced a function, this is the non-dimensional function which is equal to radiosity j divided by sigma t power 4. Okay. So, so the governing equation for the radiosity then becomes, this will be a function of zeta, and this will be equal to epsilon 1 minus epsilon 0 to capital W now zeta prime d zeta prime 1 plus okay. So, we have just non-dimensionalized the radiosity using these non-dimensional parameters. Okay. Now, how do we solve it? So, we will use method of successive approximation. So, method of successive approximation, where we have to make a guess. So, our in this case phi is basically this function, and the first guess for phi 1 will be equal to epsilon, okay, the function f. Okay. So, the first guess we make is the phi 1 is equal to epsilon. So, second guess for this function will be equal to epsilon plus half 1 minus epsilon, okay, and then integrate it over 0 to capital W. So, we substitute it here, it is constant, so epsilon d zeta prime, and then in the denominator 1 plus zeta prime minus zeta square power 3 by 2. Okay. So, this is a simple integral, we can solve it, and this gives you the value as equal to W minus zeta under root 1 plus W minus zeta square plus zeta root 1 plus zeta square. Okay. Now, because of symmetry, the radiosity of the two plates will be similar. Okay. Now, we can integrate this for the third time, it is possible by putting the second iteration into the integral, but the integration becomes quite complicated. So, we will not evaluate psi 3, okay. It will be very complicated to evaluate the integral, we will just approximate the solution by this relation. So, the value of j is equal to j1 is equal to j2, both are going to be similar because of the symmetry, is simply equal to sigma t power 4 the non-dimensional radiosity. Once the non-dimensional radiosity is known, we can easily solve for the heat flux q as a function of r. Okay. So, this was the method of successive approximation. The next method is the method of numerical quadrature. This is a very powerful method which can easily be implemented in any computer. Now, the method of numerical quadrature is very popular in radiation. So, what this basically includes, suppose we want to solve for an integration numerically. So, we have a function f x that we want to integrate from limits or boundaries a to b. So, what we do is we write this integral as a algebraic sum or weighted sum of the value function value f at selected number of node points. So, we evaluate the function at selected number of node points and we multiply by weights and then sum over those points, and that is what basically this integral. For example, let us say we want to find out the area under this curve. Okay. This area will be equal to integral f x dx from whatever limits a to b, let us say. Now, what we are saying is we have selected few number of points on this, we know the value of the function at these points, and the area can be calculated by based on the value at these points multiplied by some weights assigned to each point. Okay. Now, these points may be equally spaced, that means these points may be equally spaced or they may not be equally spaced. Okay. If they are equally spaced, the method of numerical quadrature based on this approach is called Newton-Cotes quadrature, and if the location of these points is optimized based on either Legendre polynomial or Chebyshev polynomial, this method is called accordingly the Gauss-Chebyshev quadrature or Gauss-Legendre quadrature. In short, it is called basically the Gaussian quadrature. So, Gaussian quadrature is different from Newton-Cotes quadrature in the sense that the points used to evaluate this integral are optimized according to the problem. Okay. So, we can apply this method easily to evaluate the integral in the Fredholm's equation. So, what we do is, let us say we have a one dimensional problem where the limits are a to b. So, the kernel function has to be integrated from a to b. So, we approximate this phi r is equal to f r, the term in the integral is approximated as per the formula given above, b minus a by 2 weights w j, then summed over 1 to n. Now, n is the order of quadrature, we may have 4 point quadrature, we may have 8 point quadrature. So, mostly 8-point quadrature for Gaussian works fine. So, the value of n can be then 8, then the kernel function evaluated at the nodes r j and the function phi also evaluated at the same nodes. Okay. So, this converts this integral into an algebraic equation, which is very easy to solve. Okay. Once we know the weights and we know the function values, we can solve for this equation. Now, we can write down this like this: phi r is equal to f r plus summation over phi capital phi j r and then small phi r j. Okay. So, we have defined this term as including the b minus a by 2 as capital phi. Okay. So, our equation now reduces to this simple equation, which is a system of linear equation, and the unknowns are phi, okay, at the respective quadrature points. Okay. So, based on this, so we have phi 1, phi 2, phi 3 and so on as the unknown. Okay. And we can solve the system of linear equation very easily, and the method works very fine. Okay. So, just a quick look how basically we are doing it. Suppose we have an enclosure like this, how the problem is different from finite number of surfaces and finite number of quadrature points. In finite number of surfaces, we divide this enclosure into finite number of flat surfaces like this. Okay. And we calculated average heat flux over the entire surfaces. Now, in this case quadrature, we are not selecting flat surfaces, we are just taking the quadrature points, okay, and evaluating our function at those points. Okay. And we assume that if we evaluate the quadrature in this way, we can approximate the heat flux over the entire enclosure. So, this method is much more accurate than the method used by approximating the enclosure with flat surfaces. So, I will show you one graph explaining the accuracy of this method. So, on this graph we are plotting the non-dimensional heat flux for the same problem that we have just solved, two infinite parallel plates. The x axis is non-dimensional x and y axis is non-dimensional heat flux, and we see that solid line is the exact result, and the exact result is in good agreement with the quadrature result, numerical quadrature results, with 5 points taken, 5 nodes taken. On the other hand, the successive approximation method and the kernel approximation methods are not that accurate. Okay. So, the two methods are quite involved mathematically, difficult to solve, and they are not in good agreement with the exact results. On the other hand, the quadrature is a powerful technique that gives you good results, and it is easy to solve on computers. So, thank you for your kind attention. In this lecture we learned an accurate technique to find heat flux without approximating the enclosure with flat surfaces. In the next lecture we will learn something about specular reflection. Thank you.